Okay, the last section in Chapter 5 is independent events. So what we're looking at here is understanding what independent events are and then solving problems that involve them. So it says the Fortin family has 2 children. Cam determines the probability that the family has 2 girls. Roshana determines the probability that the family has 2 girls, given that the first child is a girl. So how are these probabilities similar and how are they different? So well, first of all, without doing any solving, well, the probability that they're similar is that the fact that in each one of them, there's at least 1 girl out of the bunch. So they're both including the probability of having girls. How are they different is what we're going to look at once we solve this. So if we take a look at this using our tree diagram again, it's nice when you can use the tree diagram for the visual, and it'll help you with the calculations. So they can either have a boy or they can have a girl. So probability then of them having a boy is 1 out of 2, and the probability of them having a girl is 1 out of 2. So if the first child is a boy, probability of the second child being a boy is 1 out of 2. Probability of the second child being a girl is 1 out of 2. If the first child was a girl, probability of the second child being a boy is 1/2. Probability of the second child being a girl is 1/2. So Cam said he figured out the probability that the family has 2 girls, so that they had girl and girl. So the probability of having a girl on the first one was 1/2. Probability of them having a girl on the second one was also 1/2. So probability of both children being girls was 1/4. So Roshana here, she calculated the probability that the family has 2 girls, given that the first child is a girl. So there's 2 girls, given that, so that means the second child is a girl, given that fact that the first child was a girl. So we know from that last section, the probability of first one being a girl and the second one being a girl. To find out this one, then we need to divide out the probability that the first one was a girl. So this was what we did with dependent events, the formula that we used. It was kind of tweaking the normal formula that we use and using it this way. So probability that girl 1, or the first child's a girl and the second child is a girl. Well, first child is a girl is 1/2. Second child a girl is also 1/2. So that would be 1/4. I'm dividing that by the probability that the first child was a girl. So first child was a girl was 1/2. So that's the same as 1/4 times, if I'm dividing by 1/2, I'm multiplying by 2, so that equals 1/2. So our probabilities are a little bit different because that second one has that condition on it. So probability that both of your children that you have as a girl is 1 in 4. The second one, because they're already saying, okay, you have a girl already, that one is done, so then you already increased your chances of having 2 girls because you already know your first child is a girl. So that makes the chance of that happening increase to 1/2 or 50%. So underneath here, just a little summary, probabilities of events A and B. So in the general case, if you have probability of A intersect B, then what you're looking at is a probability of A times the probability, whoops, carried away with my swirls there. So probability of A times the probability of B given A has occurred. So it says, note events A and B are independent if when you find the probability of B given A, it's exactly the same as the probability of B. Okay, so they're saying they're independent events. So one doesn't matter what the other one is because probability of B given A is just the same as probability of B. Okay, so if I look here, probability of B given A is the same as just the probability of B happening. So probability of a girl 2, or the second child being a girl given the first child was a girl, was exactly the same as the probability that your second child was a girl. So they're both 1/2. It says for independent events, probability of A and B happening is the same as saying probability of A times the probability of B. So example 1 says a die is rolled 3 times. What is the probability of getting a 5 on all 3 rolls? So if I do this again with the tree diagram, I'm looking at probability of 5 and the probability of not getting a 5. So what is the probability of getting a 5? Well, it's a fair dice, a normal fair dice, so that would be 1 out of 6. Probability then that you won't get a 5, well, you have a 5 out of 6 chance that you won't. So on the next roll, what is the probability that you get a 5 given that the first roll was a 5? So again, we're looking at that 5 and not 5 on the second roll. Well, it's not dependent on what happened the first time, so that means that you have a 1 in 6 chance of getting a 5 on that second roll, and a 5 in 6 chance of not getting a 5 on the second roll. If your first roll wasn't a 5, then on your second roll, you have a 1 in 6 chance of getting a 5, and a 5 out of 6 chance of not getting a 5. So now your third roll. What happens with that third roll given the first 2? So if your first roll was a 5 and your second roll was a 5, what are the chances of getting a 5 or not getting a 5? 1/6 and 5/6. If your first roll was a 5 and your second roll wasn't a 5, what are the chances of getting a 5 or not a 5 in the third? 1/6 and 5/6. So it's not affecting. It's not like once you've rolled that 5, you erase it and you can't get it anymore. So then if your first roll was not a 5, your second roll was a 5, your 5 and your not 5s are 1/6 and 5/6. Not a 5, not a 5. So third roll, you have 2 options, getting a 5 or not. 1 out of 6, 5 out of 6. So what are the chances then that you got a 5 on all 3 rolls? So this is probability of a 5, and a 5. So if I multiply those, or if I take a look at those, because it's saying 5 and 5 and 5, that means I'm going to multiply. So if I take a look at my nice little tree here, probability of 5 was getting 1/6, probability on the second is 1/6, probability of getting a 5 on the third is 1/6. So it's 1/6 times 1/6 times 1/6. So that's 1 out of 216, which is 0.46%. So it's a pretty slim chance. You don't even have a 1% chance of getting a 5 in all 3 rolls. So what is the probability of getting at least 1 5 on the 3 rolls? So what you're looking at is at least 1. So at least 1 means that, well, the probability of anything happening is always between 0 and 1, so we have 1 minus what we're going to do, so at least one means that you would get none, right? The opposite of getting 1 5 is getting no 5s. So what is the probability of no 5 happening? So this is 1 minus no 5 happening in all 3 rows was 5 out of 6, 5 out of 6, 5 out of 6. So this is 1 minus 0.579, which is 0.421. So 42% chance of getting at least 1 5 on there. So the C part says, what is the probability of at most you have 1 5 on these 3 rows? So that means you have 2 things. You're either going to have no 5s or 1 5. So that or means I'm going to add them. So probability of at most 1 5 happening is the probability of getting no 5s or the probability of getting, just that 1 5. So probability of no 5s, that was this 5 6 times 5 6 times 5 6. So that was 0.579 plus probability of getting 1 5. So if I got 1 5, then that means, let's say the first row I had got 1 6. So then the other 2 rows would be 5 6 and 5 6 chance that I didn't get that. So that's getting a 5 on the first row. But let's say I didn't get a 5 on the first row. So then I would have a 5 6 chance of not getting a 5 on the first row, but I got it on the second row, so that's a 1 6 chance, which means then I wouldn't have got one on the third row. So it's 5 6 times 1 6 times 5 6. So I'm doing that again. So that's 2 times I'm doing that. So I've done it so that I got one in the first row, and I'm doing that, okay, what if that 5 came on the second row? So now what if it came on the third row? So on the third row, that would be a not 5 on the first, so that's 5 6. Not 5 on the second row, so that's a 5 6. But a 5 on the third row, so that's a 1 6. So I've actually now multiplied those 3 possibilities 3 times. So this is 3 times those possibilities. So this is equal to 0.579 plus 3 times 0.347. So that equals 0.926, which is 92.6%. So the possibility or the probability of getting at most 1 5 on there is a 92.6% chance. Okay, example 2. It says randomly select 1 bill from pot A and then 1 bill from pot B. So what is the probability of getting a 10 bill on each draw? So if I look at pot A, probability of getting a 10 on my first draw, let's put that in the wrong spot, that should be my 10. So probability of getting a 10 and probability of not a 10 is 1/3. Probability of not getting a 10 is 2/3. So that's from pot 1. So I've got my first, taken out of my first pot, then out of the second pot, probability of getting a 10 and not 10. So this is pot 2. probability of pulling a 10 out of pot 2, well, there are 2 10s out of 1, 2, 3, 4 bills. That shouldn't be a 0. I think that's supposed to be a 50, but it must have got chopped off. Same thing there. So I have 2 10s out of 4 bills. So probability of not getting a 10, that means I've got these other 2, so 2 out of 4. If the first one wasn't a 10, then the probability of getting a 10 out of the second pot is 2 out of 4. Out of the third pot is, or not getting a 10, or sorry, not the third pot. Probability of not getting a 10 on the second pot then is 2 out of 4. So this says, what is the probability of a $10 bill on each draw? So probability of getting a 10 on the first was 1/3, and the probability of getting a 10 on the second was 2 over 4, or 1/2. So that is 1 over 6, which works to 16.7%. So you've got a 16.7% chance of drawing 2 10s. So B part says, what is the probability of getting a 10 bill on only one of the 2 draws? So you can get a 10 in the first draw or a 10 in the second draw. So probability of getting a 10 on the first draw, we have a 1/3 chance of getting it. So then that means the second draw from the second pot you wouldn't get it, so that would be 2/4. So that's if this is first bill. Then the other option you have, is, okay, I didn't get a 10 in the first bill, but I got a 10 in the second bill. So if I didn't get a 10 in the first bill, the first draw, that means I had a 2/3 chance of not getting a 10, but to get a 10, I had 2 out of 4. So I have 1/3 times 2/4 is 1/6 plus 2/3 times 1/2. If I reduce that, so that is going to be 2/6, which is 1/3. So 2/6 plus 1/6 is 3/6. So it's a half. So based on the way those pots are stacked, I have a 50% chance that I'm going to get at least $1 bill, or one $10 bill. Example 3 says a pot is randomly selected, then a bill is randomly selected. So it's not saying you have to get one from pot A first and then pot B. You could do pot B first and A. So it says, what is the probability of getting a $10 bill? So this time, I have to select pot 1, or sorry, I guess that's pot A, or I have to select pot B. So what are the chances of selecting pot A? Well, I have a 1 in 2 chance of selecting pot A. And I also have a 1 in 2 chance of selecting pot B. So if I were to select pot B first, getting a $10 bill, and not getting a $10 bill, so getting a $10 bill, I have a 1 1/3 chance. Not getting a $10 bill, I have a 2/3 chance. If I happen to have selected pot B first, to get that $10 bill, I have a 2 out of 4. To not get the $10 bill, I have another 2 out of 4 chance. So what is the probability that a $10 bill is chosen? Well, so I have to pick a $10 bill, and it's just saying 1, from A or B. So probability of it coming from A Well, there's a 1 in 2 chance I'm picking pot A, and if I pick pot A, there's a 1/3 chance I'm going to get that dollar bill. Or I could pick pot B. So if I pick pot B, that's 1.5 chance, and I have a 2 out of 4 chance of selecting the $10 bill. So this is 1/6 plus 1/4. So that's same as 2/12 plus 3/12. So 5 out of 12 is equal to 41.7%. So you have a 41, almost a 42% chance that you're going to pick a $10 bill, if it doesn't matter which pot you choose from first. So B says, if a $10 bill is chosen, what is the probability that it came from pot 1? So it's saying you're getting a $10 bill, you're getting a $10 bill. What are the chances it came from pot 1? So pot 1, given that it's a $10 bill, is what we're looking at. So probability that it came from pot 1, given that it's a $10 bill. So that's saying, what's the probability that it was a $10 bill and from pot 1? Given the fact that over the probability that it is a $10 bill. So probability it's a $10 bill and from pot 1. So $10 bill, or pot 1 and $10 bill, or switch to pot 1. It was a pot 1 before? Sorry, pot A. You have a 1/2 chance of getting pot A and 1/3 chance of getting a $10 bill. Probability of getting a $10 bill. So we have 1/2 times 1/3 for pot A. Or 1/2 chance picking pot B times that 2/4 that it's a $10 bill. So this is equal to 1/6 divided by 5 over 12, because that's what we figured out in the first one. That probability of that $10 bill was at 5 out of 12. So I have 1/6 times 12 over 5. So that leaves me with 2/5 or 40% chance that I'm going to get, or that if I had a $10 bill, that it came from pot 1 or pot A. So our summary here: if the probability of event B does not depend on the probability of event A, then those are independent events. Tossing tails with a coin and drawing an ace of spades from a standard deck of cards. So if that's the two things you're looking at, they're independent of each other. Doesn't matter what that coin toss is, it's not going to affect what you draw from the cards. So it says the probability of two independent events happening is a product of their individual probabilities. So if they're independent and you want to see probability that they both happen, so A and B are happening, you just multiply the two probabilities together. So again, a tree diagram helps you to figure out the probabilities so that you can do your calculation. Drawing an item and then drawing another item after replacing the first item results in a pair of independent events. Okay, so independent events don't need to be doing two different things or selecting from two different pots. It can be using that same deck of cards but putting the cards back.